Well, hello, pre-calculus students and seekers of general truths. In this video, I would like to show you and explain Pascal's triangle. First, a quick note, it's named after the mathematician Blaise Pascal, but he's not really the one who created it or discovered it. We're not exactly sure where it started, but he's the one who maybe popularized it and showed some of the unique features of it. So Pascal's triangles look something like this. It's actually a triangle of numbers. So at the top of the triangle, we write the number 1. And then in the next line, we write 2 number 1s, okay, that are on each side of the first number 1. And then for every single row that comes after this, okay, so this is kind of our basis point here, but every single row that comes after this, the far left and the far right start and end with a 1 always. This number in the middle comes from adding the 2 numbers above. So this number here comes from adding these 2. So in this case, this is a 2 because 1 plus 1 is 2. Right? The next level of our triangle goes as follows. The far left and the far right, we have a 1. Here, right, this spot comes from adding the 2 numbers that's above. So in this case, we get a 3. So 1 plus 2 is 3. Same with this slot here. We want to add these 2 numbers, and that gives us a 3. All right, now I'm going to go a few more levels. So far left, far right. This spot here, add these 2, we get a 4. Add these 2, we get a 6. Add the 2 numbers up here, we get a 4. Okay, and as you see here that when we go down and we continue to build, we end up with something that looks more and more like a triangle. Right? This general shape here is a triangle. Okay, now the better question and the better point that I want to make here is, why does this matter? Okay, well, let's add one more little detail to this, and let's suppose that we can number each of these rows. Okay? So think of this as a table that is jagged and asymmetric. So this is the very top here is row 0. Right? The next level here is row 1. Right? And then row 2, 0, 1, 2. I got that off track here. So this is row 2. Let's try this again. This right here is row 2. Right? This is row 3, and this is row 4. Okay, so row 0, row 1, 2, 3, and 4. Okay. All right. And then let's look at each of these columns. Columns, we're also going to start at 0. So at the first row, we only have one column. So this is column 0. In the second row, this is column 0. This is column 1. Okay. This is column 0, 1, 2. Row 3, we have 0, 1, 2, 3. Okay. And row 4, we have another column, 0, 1, 2, 3, 4. Okay. So let's think about this for a moment and add a little more detail to this. So this right here, this spot right here would be row 3, right? Column 0, 1, 2. Row 3, column 2, okay, is 3. Now, you can check this in your calculator. 3 choose 2 is precisely equal to 3. Okay? And then here, this is row 4, right? Row 4, column 0, 1, 2. So 4 choose 2 is precisely equal to 6. Okay? So, and this works for every single part of Pascal's triangle. Namely that if we go to the row and the column in Pascal's triangle, we found the value of combinations. Before the advent of calculators, there was this this triangle here, this is how people calculate combinations. And it's actually an elegant solution because you could build this table really quickly by yourself using some basic addition, and then you can use that to calculate some really, really large numbers. Right? Now, even today, even if we have a calculator, Pascal's triangle is still very useful. For example, if I asked you to expand, let me give you another side example here. If I asked you to expand this expression, I don't know, x plus y raised to the 5th power, right? We know with the binomial theorem that we're supposed to go 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and that's going to take a while to actually type it all in with a calculator. But if we think about Pascal's triangle, let me add row 5 here. Row 5 here would be, this would be a 1, 5, 10, 10, 5, and then 1. Okay, so the binomial theorem tells us that the coefficients is going to come from 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. Well, rather than typing that in a bunch of times to a calculator or a computer, we can actually extract it really quickly, right? So the first coefficient is going to be 1, x to the 5th. The second coefficient is going to be 5, x to the 4th, y to the 1st. Next coefficient is going to be 10, x to the 3rd, y to the 2nd. Right? Coefficient after that is going to be 10, x to the 2nd, y to the 3rd. The next one after that is going to be 5, this coefficient here, 5 choose 4, x, y to the 4th. And the last coefficient here is going to be a 1, x to the 0th, y to the 5th. Okay? So even with a calculator, I mean, I can challenge anybody, you know, you can use your calculator to calculate, to expand something like this, right? Or you can use Pascal's triangle, and actually using Pascal's triangle is significantly faster. Okay? Now, one of the things that we're going to explore together in the notes, videos, and some of our homework exercises is, why does this triangle work? Why does this triangle thoroughly explain for us combinations? Okay? The other thing I want to point out too about this triangle is, notice the symmetry here that happens, right? That 4 choose, this is row 4, for example, 4 choose 1 and 4 choose 3 are exactly the same. So the left side of the triangle and the right side of the triangle is identical. And this goes back to the concept we had before, that if I have 4 people and I'm choosing one of them, then that's the same thing as saying I have 4 people and I'm choosing 3 people to eliminate, right? To choose one person is exactly the same thing as to choose 3 people to eliminate, all right? And we can go down the triangle and we can see the symmetry happening at every single row. And that comes back to this idea that n choose r. If I have n items and I want to choose r of them, then that's the same thing as having n item and choosing n minus r items to eliminate. Okay, so Pascal's triangle, factorial proofs, combinations, common sense, and making these connections, they all start to come together at this point. And hopefully you start to see how these things are related. And one of the big ideas in combinatorics, in counting, is how do we view a problem from multiple different ways? And how do we reconcile their similarities and differences? If you get a good sense of how to do that, then you are on the right track. Okay? And as I said, we're going to end this video, this lesson here in terms of the videos, but we're going to explore a little bit more about Pascal's triangle, and we're going to see why is it exactly that this triangle works, and why is it exactly this triangle is connected to combinations. As always, keep working hard, ask for help when you need it. Thank you for watching, and have a wonderful day.